coming to this session 9, and we will discuss mostly the in this session we will learn mechanical properties. It's not even mechanical properties, we will just revise what we have done. And why I'm revising is because the assignments were given. I think they have we uploaded correctly, but I guess there is a lag. See, while we were discussing thermal properties, so we are going to discuss the thermal properties. Okay, we are going to discuss the thermal properties, and sir has done a simple miscalculation. So we will okay, sorry, we will not we will I will clarify that. And also, yeah, he made wrong at few steps. We will do that shortly. Okay, so there is no need to worry about. And yeah, that's all. So why we are going to discuss the mechanical properties is, and because to just have a brief recap so that you can solve the assignment sessions, right? Now coming to stress and relations. So why do we need a stress strain relations? Either it is whether you call it engineering stress or engineering strain curve, or engineering strain and engineering stress curve. So anything of the sort. Okay. So why do we need that? That is the thing we want to understand. So for that you need to know what are the things that we get from it. First, you will get the elastic region, and from elastic region there is this simple relation. You will get Young's modulus, right? Now, it's just a slope, right? So there is no rocket science here. So it's just a slope, and after that there is this thing. Okay, so now here you have the stress strain relation, and then here you have the curve, and if you fit it, you will get, suppose there is a constant k and power n, and there is a strain, right? And then you will get the flow characteristics of that curve, right? That is also another point. And what else is there? Okay, so one is the flow characteristic, and at this point you will get the ultimate tensile strength, right? And you will get the ductility, the other thing. So you will get the ductility, right? And you will also get the toughness. Toughness is nothing but the area under the stress strain curve. That will give you toughness. So that will tell us what is the toughness of the material. So how tough our material is. So that is the one thing. And you will get an yield strength. So strength is defined in two terms. One is the ultimate tensile strength, another is the yield strength. So whenever you talk about the strength of the materials, so we take strength from two terms. One is the yield strength, from where the material is starting to plastically deform, and the ultimate tensile strength, what is the maximum load that a material can take. So strength comes from these two terms. Okay, and yeah, so that is one part. Right, so if there is an UTS, yield strength, and what else is there? I guess, yeah, and there is a fracture. What is the what is the total strain in a material until it gets fractured, right? So that tells you about the ductility. And toughness, again, rest area, rest stress strain curve. So all these parameters can be obtained from a simple stress strain curve. So that's why we need our stress strain curve, right? And the next one is the hardness. Now, how hardness defines our things, right? So for example, if you have a chain, so a gold chain. So gold chain, if you do any elongations, or like if you try to stretch it, then it will stretch, right? It is not as hard. And if you even try to scratch it with something, you will get scratches. But for example, if you have ball bearings, so ball bearings shouldn't be ductile. If they are ductile, then your whole the rotating mechanism will break. They need to hard, because they undergo a lot of rotations, right? They undergo very much because shear in it. So for that you need to have a hard material. So that's coming from hardness. And effect of temperature on properties, how the temperature will affect our deformation, right? So temperature is nothing but you are supplying energy, heat energy. So for a material, any material to deform, you need to apply some amount of energy, right? If you already have that heat energy in terms of the energy in terms of heat, then there is no need for you to give the extra stress, right? So that is the effect of temperature. And the fluid properties, this is mostly related to the semi-fluids where the material starts to behave like a fluid, right? So yeah, and viscoelastic behavioral formats. This is not needed for this mechanical properties, right? For nanomaterials. So we will just stop it at here. Okay. Yeah. Here we came the stress strain curve. In terms of stress strain curve, you will know these are different points. The strength you will know what are the different types of strengths, the yield strength and the UTS. That is one point. So all these things can be found out from a simple stress strain curve. And the next thing, yeah, and then we have mostly discussed this part, right? So mechanical properties of a nanomaterial. So we will come to this in a few minutes. Okay. So before that, we have discussed Hall pitch correlation. It is like a very, how do you say? It's like a metallurgy 101. Whenever you study the introductory course to material science, you will come across this relation, Hall pitch correlation. Now, what does it say? It tells you the relation between the yield strength, or just I have said before, the is the amount of stress that required to either you can say that initiate the plastic deformation or start of the plastic deformation, right? So that is sigma, and that is given as, I will just represent it as a yield strength, okay, ys, and then that is proportional, that is inertially proportional to grain size. So that is what we learned from Hall pitch correlation, and I'm not going to derive, but I will give just a recap of how did we derive, right? So for example, if I have, this is my grain 1, this is my grain 2, and the atomic planes distribution is like this, and here the atomic planes distribution is flat. Okay? So you can see the the angular rotation, right? So this is the angular difference between these two planes, right? And see, for this you need not to assume so many things. That's why I have said we didn't derive it, but still. So you need not to assume so many things. What all you need to think is the dislocations are getting piled up. This thing we have heard many times, so I hope please bear with me. And then for these dislocations to move here, there must be something which should initiate. Right. Now, for these dislocations to move there, they need to change the direction. Right. How do they change the direction? So for that to happen, there must be someone who should initiate first dislocations here. Right. So for that to happen, so let's say there is a source, fragment source or any type of dislocation source, which will initiate the dislocation motion in this grain, so that the dislocations from here can come from cross grains, right? So that is the thing. Now, what is the stress? This is the applied stress, right? So I will write it in separate thing. This is the applied stress that we are applying. Okay. Let's say this is my critical stress that I require, and whenever you try to apply a stress, it will resolve. It will resolve into components, right? And what are those components? We have one normal component and one is shear component, right? So the plastic deformation, we take the shear component, right? Because the normal components are just the elongation and compression. We do not want them. So for now we will take only the shear component. So applied shear stress, not the, you can say shear stress, or you can even call it as, remove it everything. This is my grain 1, grain 2, and the applied shear stress is critical resolved shear stress, resolved shear stress, right? So this is my resolved shear stress. Okay, now, and there is another stress which is the lattice friction, or you cannot call it as a so you know the Newton's third law. For every force there is an equal and opposite force. So there is also a drag. For example, if something, if a ball is moving in air, it will feel drag because of air, right? So that is a common thing. So the same here is, whenever a dislocation tries to move, it will see uh, lattice friction, right? More or less. So dislocation is more or less nothing like a moving man, okay, or moving car or anything. So there is a friction from the road. Right? So same, the friction is from the lattice. Lattice friction, right? Now, what is my shear strain? Shear strain will be equals to, right? So how many Burgess vectors are there? So each dislocation will move one Burgess vector. So whenever a dislocation will move, it will move one Burgess vector, right? And there are n dislocations. So, and what is the total length? Total length of the grain, because the dislocations are moving from one point of the grain to another point, right? So from one point to another point. Now what is my shear stress? Will be equals to Young's modulus n v from L. Right? Now, what should be my critical this stress required to initiate our what do you call this dislocation here in grain 2, right? So for that you need the applied minus the, that is friction, should be equals to tau star. That is one relation. This is the applied or resolved shear stress. This is the another relation. From this you can derive. I already derived this. This is just to make sure that you know how the dislocations are moving from one grain to another grain. That is the mechanism of it, right? So I hope I don't need to prove it again. Okay. So it is simple. Right? Only need to, yeah, there is another relation that you need to prove. Okay. This is one relation, this is another relation. So all you need to do is just substitute it and you will get it. Okay. So there is no need for big things, right? So yeah. Applied stress, yeah. So it is okay. And then let's move on to the next thing. So this is my, so what else we have discussed? And then we have discussed the hardness. So how did this hardness came? So hardness will tell us about how the material is scratch resistant, or how the material is not included for instant deformation. So that's what we have seen, right? And so did we do any mistake in the last slide? This one. So first thing is you have so critical stress required will be equals to, so yeah, there is another relation. So this you need to understand. The another relation is tau what? So tau star will be equals to, because you have 4 variables, right? We need another variable. We need another equation. 3 variables, right? So we need 3 equations. Then you can easily solve. So this tau is, oh wait a minute. So resolved shear stress, yeah, there we have made a mistake. So tau star will be equals to n times tau s, or tau resolved shear stress. Resolved shear stress is nothing but uh, it is a shear stress that is required to move one dislocation. So why do we need resolved shear stress, right? So that is one thing. So all we know is deformation happens in terms of slip planes, right? So whenever for edge dislocation, we have already saw this, right? So the dislocation will move like this. So that means the bottom atomic planes are sliding over the lower atomic planes. So the bottom atomic planes, these are the set of planes that are sliding over. It looks like this, right? It is not actually the thing. Not all atomic planes are moving. Again, it will be impossible. Only one atomic plane at a time. It is getting the dislocation is getting moved, right? That's how it happens. So it looks like physically it looks like the bottom atomic planes will move on a one step, right? So that's why you see steps at the end. Whenever a material totally deforms or a dislocation moves from one end to the other, you will get steps. So that's what happens. Now, if you have a material, you apply stress, then my slip system is like this. Okay, then this guy will slip over this guy. That's why we take the resolved shear stress. Okay, I hope now you people can understand why the importance we use the critical or resolved shear stress. Right. So this is our stress which we resolved it into the atomic planes, so that we can have this slipping motion can be easily defined there with the equations, right? So that's why the tau star will be equals to tau RSS, resolved shear stress, times the number of dislocations, right? Now, and then the other relation was tau RSS, resolved shear stress will be equals to the applied shear stress, the applied stress, not shear stress, the applied stress minus the lattice friction, right? So when you come above it, then only you can able to move, or then only you can able to move or slip, or dislocation can move. If you cannot even if you cannot have a value greater than your friction value, then you cannot move, right? So if you can dominate the friction, then only if your applying force is greater than the frictional force, then only you can move, right? So that's how we move on Earth also. The same thing goes for anything. The force should dominate the frictional stress, or should more than the frictional stress. Then only, same here. If your applied stress is more than the lattice friction, then only the dislocation can move. So that dislocation motion is given by the resolved shear stress, and that is equals to n times of dislocation, n times of tau, and that times n will give you the critical stress that needs to get in a second grain for them to move, right? So this is one relation, and yeah, again the same resolved shear stress. It is here tau star equals to n tau RSS, and here you have third relation. From this, if you substitute first this guy into this guy and then this guy. Okay, so first you substitute this guy here, then you substitute n here, then you will finally have your value. Okay, simple. Or you can just substitute n value here. You will have tau RSS square. And we do not want n in our thing, because we cannot measure or count the number of dislocations. So you can eliminate n from here, right? So that's all. And then there is the hardness we have discussed. So then we have different types of hardness testing. Because hardness, Rockwell hardness, it depends upon how strong the material is, right? So there is a scale called Morse scale. And the strongest will be the diamond, and then you will have some other minerals. Okay, so you can just refer to that. It is basically more intended for the pure mechanical properties of the materials, so mechanical metallurgy, right? So you do not have to go into that depth. This is mostly about the mechanical properties of nanomaterials, right? So again, we had all this pain to understand this Hall-based correlation, but still, this Hall-based correlation cannot be applied to nanomaterials. And I know, and I hope you all know after seeing those lectures, because if the grain is very small, then how can you accommodate the dislocations? Because the line defects are lengthy, right? They are very long. And if you have a nanoparticle, how can you accommodate a dislocation? Right? And for example, even if you have a nano rod or a nano CNT, how can you accommodate dislocation? Right? Because it is a thin sheet, right, coiled around, which is called as CNT. So you cannot accommodate defects there because they already have very high amount of surface energy. These defects cannot be sustained there. Why? Because you already have very high surface energy, so the system is at a higher energy state. And whenever you try to include dislocation there, and these dislocations have a strain energy around it, or strain fields. These dislocations have a strain fields around it. Then that means you are increasing the energy of the system, further increasing the energy of the system. And if it is the case, then energy will not take it. Right? It will just reject that energy. So that's why you will not find defects. You might find vacancies, but finding dislocations in nanoparticles and CNTs is not possible, right? Because the particles are so small, you cannot find dislocations. Now, and that is about the mechanical properties, and because of this, you will have the inverse Hall-based correlation, where after some point, here you can see. So hardness will keep on increasing, right? It will increase, and then after some point, after once you reach a nano range, this guy will go down, right? So, and why that thing happens? Why? Because you, first of all, you do not have defects there, and these particles are so small, and the surface energy is so large, they will start gliding, or you will have a grain boundary sliding. Okay. So these particles will just slide on each other, and you will finally have your deformation. So that's one point, right? So that's why you will have the inverse Hall-based correlation. Okay. So everything in the nanoplane is different. It will not be as same as the, how do you say, the mechanical properties of bulk solids, right? And then, yeah, so everything is done. So moving on to the thermal properties, right? So what do I mean before going into this? I'll last add one more slide. Okay, so when I say about thermal properties, so what do I mean? So thermal properties are more or less intends to tell us about how thermal energy is being accommodated or being transferred inside a system. Either it is isolated or in connection with surroundings. Right. So So this is what we meant by thermal properties, right? And in this thermal properties, you will know we have been studying from like what, class 12, class 11, right? So whenever you talk about thermodynamics, sorry, not thermodynamics, whenever you talk about the thermal properties, the first thing you will hear is types of thermal energy transfer, right? And what are the different things that you see? The first one is conduction, second one is convection, third one is radiation. See, it is basically these three things are derived from how the system is behaving. Okay, so if our system is rigid or hard material or metals, then we came up with the term this guy, conduction. So it is for rigid systems. Right? So there is a matter here, some sort of matter. Matter is nothing but made up of atoms, right? So but the matter itself is rigid, so it will not deform. The second thing is, if you have a matter and if that matter is deformable, right? And that where you will have fluids. What do you mean with fluid? Fluids are those, whenever you try to deform it, they will try to accommodate that energy. Right? But solids cannot accommodate those energy, right? If you try to deform, they will deform. Right? So they cannot accommodate those energies. Now, and the third one is, if this is about matter, rigid systems contains matter, solids, fluids contains matter, liquids, gases, and others. What happens if you do not have matter? Right? If you do not have atoms, if you have empty space, then you have radiation. That's it. This is all about the different types of energy transfer. And you can, and there is this subtle line for systems which can act as sometimes solids and sometimes fluids, such as semi-fluids or semi-solids, even semi-fluids, I guess. I don't know what to call them, right? So, yeah. Then you apply, depending upon which type of heat transfer it is taking, you may apply this to that. Okay. Now, again, we all know. So, in conduction is mostly happens in solids, and it happens in two ways. One is atomic oscillations. Two is our electron transport. Again, these two are the different types of way that you can, how do I say, you can transfer thermal energy inside a solid from T1 to T2 if T1 is greater than T2, then let's do the flow lines. Right, so heat energy will flow over lines. Okay. Now it happens to either atomic oscillations or electron transport. And electron transport mostly happens in the metals. Right? You even have atomic oscillations in metals also, but the electron heat energy transport is so dominant that you can just neglect these atomic oscillations. Okay, So why in metals? Because in metals you have the conduction band, you have the valence band, and you have conduction band. So these are the two bands which you normally see. The valence band is nothing but, and when the electrons jump from, when you supply some energy and the electrons will jump from valence band to conduction band, right, this is what we derive, right. So let's see how this goes now. And depending upon you have whether, so let's say the first thing that we see is you have valence band and you have conduction band, CB, okay. So again, please don't ask me what is band. Band is nothing but the the superposition or overlapping of orbitals, right? So not overlapping. So for example, each atom has its own set of orbitals. So for example, if I have an atom, then it has p orbitals, px, py, pz, right? So this is what we see. Sp, yeah, 3. So x, y, y, z, and zx, right? So this is what you see in p orbitals, 3 p orbitals. This is for one atom. So what if I have two atoms? If two atoms comes close together, they form a bond, then these orbitals will have certain energy levels, right? And if another atom will come and try to bond with each other, then these three orbitals will overlap and they will form discrete orbitals, not discrete, but the same energy type orbitals, right? And when there is a fourth atom coming, and it will form with bonds with other atoms, right? And again, the undergo hybridization, and you will have same state energy of orbitals. And when more and more n number of atoms comes here, they will start overlapping, or they will start, you just add them, right? So when you add n number of, n is nothing but 6 point, oh sorry, Avogadro number, right? 6.023 into 10 to the power 23 atoms comes close together, or they form atomic bonds, then these orbitals will overlap so much to so that they will form, it will look like a continuous band, right? It will not be just a straight line or a single energy level. It will look like a continuous energy levels, and this collection of orbitals is called as a band, right? And when these again come together and they overlap, they will form one set of band. And if electrons are at their ground state, and if they are called as a valence band, and if they go into the excited state, then that is called as a conduction band. And in conduction band, the electrons can freely move. Why? Because the conduction band is free of space when compared to valence band, which is always filled with electrons, right? So that's what it means. So that's why when an electron comes into conduction band, it can freely move. It can freely move and transfer energy. Logic, right? So there is nothing great to understand here. And in electronics, in electronics or in electrical properties, we define materials depending upon this band gap. And what is band gap? Band gap is nothing but the energy difference between conduction band and valence band, or we can say the this is the energy difference, conduction band and valence band, or the highest valence band energy and the lowest conduction band energy, or the highest atomic orbital um, energy of a valence band minus, or anyway minus the lowest atomic orbital energy of the conduction band. You can just assume it like that, right? So that is the energy difference and that is the band gap. And if in metals the conduction band and valence band difference is small and sometimes they even overlap, all the electrons have to do is just jump this small energy. This can even happen with even if you shine light. So that much sensitive or that much less is this band gap, right? So light has very uh, small amount of energy when compared to the electron's motion or any other particles, right? So the photon's energy depends upon the wavelength, right? And yeah, even if you shine the low energy photons like visible light, some metals may glow, right? And some materials may glow, and the reason is because that is the, the band gap between the conduction and conduction band is that much low, right? So in metals the band gap is low and sometimes it may overlap, so that's why we can easily conduct electricity in silver and gold, copper, iron and metals, right? So this is the case. The case is because the electrons are lying above the conduction band. So this is for metals. And what about the non-metals or the insulators? So this is our conductors. These are conductors, right? So that is the meaning of conductor. The energy difference is very small, or sometimes they even overlap in some metals. And then you have insulators. So insulators is nothing but the energy gap is very large, right? So that means it can be few electron volts, right? From maybe more than 4-5 electron volts. So I do not know the exact number, but yeah. And then you have semiconductors. Same, the definition itself is same. The reason is the gap is very less compared to insulators, but higher compared to metal conductors. And that is for silicon it may be 1.4 or 1.3 electron volts. I do not know the exact number. So whenever you supply some amount of energy, so that energy is supplied in the terms of heat. So whenever you take silicon wafer and you do the conductivity testing, you just supply current, the current will not pass through at lower temperatures. So whenever you try to heat this silicon wafer, then due to thermal energy, the electrons will jump from valence band to conduction band, because we are supplying the heat energy, and they will start conducting. So that's how it is. For this, the resistivity versus temperature, and the best way to define the metals, metal difference between the conductors and semiconductors, if the resistivity increases with temperature, then you call them as a conductors, and if the resistivity goes down initially with the temperature, you call it as the semiconductors. The insulators, they doesn't conduct electricity, right? Because the band gap is so large, either you melt them or you supply high amount of energy, it will not happen, right? So yeah, that's why the electron transport is more dominant in our metals or conductors, right? So that's why we also need to make sure if the electrons in conduction band, then that material can conduct more thermal energy when compared to the material with only the atomic oscillations, right? And yeah, so atomic oscillations, how the atomic oscillations happen? The atomic oscillations happen by few atoms, I mean the group of atoms start vibrating at a certain frequency, and that is called as a phonon. And phonon is a quasi-particle. See, there is a difference between the quantum particle and quasi particle. Quasi particle, we call them a quasi particle. Again, the difference between not the quantum particle, the particle and quasi particle. The particle in itself suggests one. Right? We have one particle, one nanoparticle, but not the quasi particle. Quasi particle is nothing but the collection of those particles. Right? So photon is a particle. Or I cannot say, yeah, you can say particle because the duality, right? So phonon is a particle, a single one. Electron is a particle, a single one, but not the phonon. Phonon are collection of atoms. Right? So if you can, I can define atom as one particle, right? But I cannot define 10 atoms as a one particle. Then it will become a quasi particle. That's why we call it as a phonon. That's why we call it as quasi particle, a collection of atoms. Right? So when collection of atoms starts vibrating, you call it as a phonon. Now again the question comes, okay, before going into that, before going deep into the phonon, let's just stick with other thermal properties, right? So now, so how our thermal properties will affect this? Yeah, thermal properties, you will have melting point, physical, you can consider physical thermal properties, right? So melting point, boiling point, and others. Right? The phase transformation temperature. These defines our thermal properties of your nanomaterials. So how our melting temperature will change. I'm going to derive that because sir has made us a small mistake when deriving this part. So we will do this here. Okay. So our melting point will change with the size of the nanoparticle, right? So yeah. Now free energy should be negative. For a reaction to happen, we all have studied. For any reaction to take place, we want our free energy, the total free energy, should be negative, right? And for this to negative, the free energy, solid is melting, right? So free energy of liquid minus free energy of solid should be negative, right? So we should have negative, then only the reaction is possible, because then only the solid will convert into liquid, right? So let's take, we are only considering the pure, okay? We are not considering alloys for now. Let's just consider the pure gold nanoparticle, right? Now the free energy of liquid minus free energy of solid should be negative, then that means the HL minus TMSL minus HS minus TMSS should be negative, or delta H minus TM delta S melting, right, should be equals to negative. And for at equilibrium, when solid and liquid are equilibrium, then this should be 0. Then Tm will be called as delta Hm upon delta Sm. This is one relation. Okay. So for delta G to be negative, again this delta G to be negative, first the volumetric free energy, the volume transformed from solid to liquid, right? So I mean the volume of liquid that has formed times the delta G, and that delta G is this. So if I substitute this guy here, delta G will be equals to delta H minus T delta S. And if we assume the delta H and delta S, delta H and delta Sm, delta S are not changing near to the melting point, not far away from the melting point, but because we are near the melting point, which is ideal case, and it is not true for everything, right? Because the heat capacity will change, and if the heat capacity will change, then the delta H will also change, because it depends upon integral of Cp delta T. I will write it instead of explaining. So if this is my melting point, if this is my Cp axis, then my Cp will change, and it will change again. This is solid, this is liquid, right? Or it may like go down, and it may go down, who knows, or it may remain constant, right? It can cannot go down, okay, because the oscillations are more in liquids, right? So at near melting point, very close to the melting point, the Cp is not changing rapidly, okay. Let's say it is not changing very rapidly, or it is constant, or it doesn't depend upon temperature. So if it is not changing rapidly, then that means it is not a very high dependent function of temperature, or you can just assume Cp is constant, or Cp is not a function of temperature, okay, just near the melting point. Then you can assume this one. Then you can just substitute this guy here. Delta G equals to delta H minus T delta S. So if my Cp is not changing, then delta H will same. So for example, this is my T melting, okay. So near the T melting point, my Cp value is not changing, right? Then the delta Sm will remain same, just like delta Hm. It is constant because we know del H will be equals to Cp of solid minus Cp of liquid. You can take a reverse sign, it depends upon the flow of the reaction, right? So Cp minus Cl dt, and delta S will be equals to integral of Cp solid minus Cp liquid by T dt, right? If I assume the Cp is also constant as a temperature, it doesn't change with temperature, then I take Cp out, right? Then delta H and delta S will remain constant, right, close to the temperature. Or you might say, okay, we have delta H, Cp came out, then you will have T. Delta H is a linear relation, and in delta S you have ln T. Even though if you take that, they will not change very much, right? Because the temperature, we are just seeing near the melting temperature. For example, my melting temperature is 1400, then I'm near to 1400.5. So it's not a drastic change, right? So you can just assume delta H and delta S is constant. Then you can just substitute, instead of delta S, you just substitute this relation, this guy. What is delta Sm? Tm delta Hm. Oh, sorry. So delta Sm is delta Hm upon Tm. So delta Hm, you can just write Hm upon Tm. So delta G will be delta H came, and this delta H is nothing but enthalpy of fusion at Ls times, okay, let me write it more clearly, okay. So delta Hm is nothing but Ls enthalpy of fusion, and then I have Tm minus T, which will be delta T upon T melting point. This is called undercooling. How fast, not how fast you are cooling is nothing but the cooling rate, right? We are not talking about the cooling rate, we are talking about the undercooling. Undercooling is nothing but how far you are below the melting temperature. If there is Tm and there is T, then Tm minus T, right? So for example, if my melting temperature is 0, right? So what is the melting temperature of water? Ice above 0, right? Sorry. So my melting temperature of an ice is above 0, or you can count as 0. So if I go above 0, for example, if I am at 5 degrees centigrade, then my undercooling will be 0 minus 5. 0 minus of minus 5. Or I can say 0 or 5 minus 0. Okay. Yeah, 5 minus 0 is 5. That is my undercooling. 5 degrees. Alright, so now let's continue writing this guy. Let's remove this guy for, let's not write this guy here. Okay. Now, so my delta G will be equals to minus volume of liquid form delta G V. what is my delta GV? This is my delta GV, because we are not considering any area, right? So that's why we write is delta GV. We are not considering any area here. We are just assuming a very big particle for here. So that's why we write it term delta V, delta GV plus. Now if I take areas, the first thing that comes is area of liquid times surface energy of liquid. Here you can see. So this is my area of liquid, and there is another layer of area of liquid that is inside, but that is sticking to the solid. So that's why we call it as gamma solid liquid interface, same, minus this area has been lost, right? This area has been lost and new solid surface area has been created, right? Instead of new interface has been created, right? So area of solid, now solid, simple. Now coming to derivation of, we know what is delta GV, so let's write it, whatever we know, let's write first here. Delta GV is nothing but LS delta T. And what is my volume of liquid? Volume of liquid is nothing but if this is my solid and this is my liquid, right? Solid has radius R, liquid has thickness T. So then what is my volume of liquid? Volume of liquid must be, let's say this is a hollow, okay? So 4 by 3 by R, not R. Let's take blank. Okay, so where did I make blank? 4 by 3 by R plus T whole cube minus 4 by 3 by R cube. Simple. Now VL will be equals to 4 by 3 by R cube plus 4 by 3 by, am I doing right? Yeah, I'm doing right. Yeah, that's it. And then so the bigger sphere minus the lower sphere, under one, the inside one. Then I will get the volume. And then I have okay, let's take 4 by 3 common instead of writing 4 by 3 again and again and again. Pi R cube, even let's take pi also common. So 4 by 3 pi common, R cube plus 3 R square T plus 3 T R, 3 T square R plus T cube minus 4 by 3 by R cube. This guy will get cancelled. So the terms that are remained are volume of liquid 4 by 3 pi 3 R square T plus 3 T square R plus T cube. Let's do every cancellation bit after we write our whole equation, because that will be more easy. We will know where we have missed our terms there. Right, so 4, it is okay. So we know what is my volume. That coming to the area of liquid. Now what is my area of liquid? That thing needs to be known. So what is my area of liquid? Area of liquid is 4 pi R plus T whole square, and my area of solid 4 pi R square, and my area of solid liquid interface same 4 pi R square, because this is my solid liquid interface. I will write it again. This is my solid and this is my liquid, solid liquid interface. The radius is same, right? At that point. There's nothing to worry about, so it's just the same area. Okay. Now let's do the substitution. This is the trickiest part. Delta G will be equals to minus Ls delta T upon Tm, and then you have volume, right? Volume is 4 by 3 pi 3t square r plus 3rt square plus tq plus 4 pi let's distribute this guy also. 4 pi, okay, so okay, let's do it. 4 pi r square plus t square plus 2rt gamma L minus 4 pi r square gamma S plus 4 pi r square gamma SL. That's it, right? I hope you are right. AL gamma L, yeah, AL gamma L, AS, yeah, nice. So far so good. So slide here. Okay. So let's do the differentiation part, right? And we know, and for this guy to be at equilibrium, that means the dou G by dou T shouldn't be changed, and that should be 0. So dou G upon dou T should be 0, right? Now if I do the differentiation, Ls delta T upon Tm, let's write everything. 4 by 3 pi, it will become what, 6tr plus, oh, let's see, r square, 0, right there it should be 0, and here 3r square plus 3t square, right? I hope I'm right. This 3t square, right? The only thing you will get here is 60 and now 3t. Okay, and then we have 4 pi, and if you differentiate r square it will be 0, so then you will have 2t plus 2r gamma L minus, and everything here is 4 pi r square. Right? And these guys will go away. I hope I'm not doing anything wrong. Right? So let's check it whether we are doing anything wrong here. So 4 pi r square, what is my gamma SL? ASL. ASL is same as this area, which is 4 pi r square. Okay, let's move on. These guys will go to 0, right? Obviously they will go to 0 because there is nothing t here. All you will find is r square. So then yeah, so let's write 0 here. Let's do the cancellation. You can take out 4 pi, and because it is tending to 0, you can take out 4 pi, and you can cancel out 3 times 2, 1, 1, and you will have 2 here. So finally I will have Ls delta T upon Tm pi also is gone, right? Pi, you can take out pi as common. Then I have what, 2tr 2tr plus 3, no, there is no 3, this is r square plus t square plus, if I take 2 common, it will be t plus r, that is gamma l. Right, good, nice. It is tending to 0, and you already have minus here, so minus here. Then if I take everything this side, ls delta t this side, ls delta t upon tm will be equals to 2 times t plus r gamma l, and then you have 2tr plus r square plus t square. Now how does this look like? This looks like, did we do anything wrong with the volume? No, I guess we didn't do anything wrong with the volume. Okay, so this is 2 gamma l upon, you can write it as t plus r square, and you already have t plus r, you can cancel out, and you have l as delta tm tm, which is 2 gamma l upon r plus t. Or there is one relation, and if you take another in gamma SL, then it will be 2 gamma SL upon r minus t. Okay, so yeah, you can either derive this, if you take solid, and then let's draw a clear circle. If I have a solid and if I have liquid, if I take this as r and this as r plus t, then you will arrive with that condition. Or you can take this whole as r and this as r minus t, then you will have another condition, right? So you can prove it, it's not very big deal, you know. So even if I take this is my surface, and if I write it this as my gamma SL, right? So yeah, it's no need to write anything because the whole thing is being covered, right? So, yeah. And yeah, so if we have if t tends to 0, then you will have r. So delta t is directly proportional to, inversely proportional to 1 by r. That's it. That's the relation we will finally achieve it. Okay. So delta t is inversely proportional to r, and these are those different relations. So my t minus tm is inversely proportional to r. If my r increases, this value should decrease. If my r tends to infinite, then this will tends to 0, then t will be tm, which is for bulk. If my r is very less, then this whole value will go up, then the difference should be a positive value. If my difference is a positive value, then t should be less than tm. Oh, sorry, it's not, it's tm minus t. Mistake, it is tm minus t, right? Yeah, if this value goes up, then t should be less than T, then only this value will go out. So that's what you see here. The melting point of pure gold. This is a calculated melting point, but it will start decreasing with your particle radius or the size of the gold nanoparticle. Same goes for lead, same goes for copper, same goes for silicon, same goes for bismuth. Right? You will see the melting point goes down with decreasing the size of the nanoparticle. Okay. Okay. I hope I am clear. Then let's move on to the phonons, which we were discussing in a great detail. Right? So yeah. So phonons again are nothing but quasi-particles, right? So I mean, you can come through like this, or you can define your solid, initial solid R as R. This is one way of deriving it. And initial solid, right? We didn't consider initial solid, so that's where we made a mistake. Yeah. The initial solid was what? Initial solid was R plus T, right? So yep, we did a mistake. So our initial solid was R plus T, so this must be, everything was same, the only difference was here. The initial solid also was R plus T whole square. And now the area of liquid is also R plus T. Because this is the area, right? But the area of solid liquid interface is R minus T. So yeah. Should we do it again? Yeah, we have time, right? Yeah, we'll do it. Instead of writing all these things. There's this part. Okay. We'll start with here, okay? So our initial solid has radius of R, and when final it was melted, then this is my thickness of liquid, so it is an ASL is R minus T whole square. So this guy is R plus T whole square. Now we are correct. Yeah. See, even the small things have matter here. Because you need to know what exactly you are doing. If I finally considered, the reduced size of the particle, which is wrong. I mean, mathematically it is wrong, but see, if finally the answer was same, right? So let's do that. And 4 pi R plus T whole square gamma, this is L, and then 4 pi R minus T whole square gamma. What is this guy? This guy is no, again we are doing mistake. So this this will be not r plus L. Okay, because it is r, right? The final volume, final radius is r, so it will be r square. Same. Take it out. Let me explain the problem again. I will take these things out clearly. Okay. Now, let's say I have this as r, the initial particle r, then at final point this is my solid and this is my liquid, right? So this should be my r minus t because it is r, right? So that's why my liquid will also have same radius as the solid. So gamma L minus 4 pi r square gamma s plus 4 pi r minus t whole square gamma s. Now we will just directly do the differentiation here. So if I do the differentiation for the equilibrium point, then let me write it as Tm 4 by 3 pi. You have 6tr plus 3r square plus 3t square. Here is one point. Let's continue here itself so that no confusion is there. So r square will go away because there is no t term, and the only thing that we are remained with is minus of 4 pi r minus t. Because you do the differentiation, you will remind with 2, right? So hope it is not very tough maths. And then you will have this, guys. So the volume also will change, right? The volume, the notations will change, not everything will change, only the notations will change. Okay, so the notations that are going to change are minus 3 RT square. So because I already have minus, so minus will minus become plus. This will become 3r square t will become plus. This will also become plus, but this guy will be minus. So I have 6 3r to 3r square. Now it looks nice. Now if I substitute all these terms, so let's take 4 pi out and 3 cancel everything here. 1 1. What are we are remained with? Ls delta t upon Tm. This is minus 2tr, right? So minus 2tr plus r square plus t square. And here you have r minus t to n gamma s and ls delta t upon tm. How does this look like? This looks like t minus r minus t whole square. You can take anything. T minus r whole square and r minus t whole square will give you same value because you have square, right? It will not change anything. 2 r minus t, and this is r minus t whole square. This comes so tm 2 gamma SL upon r minus t. And if my t is very small, r minus t can be approximately taken as, this is not approximate, that is congruent, can approximately taken as r. Then tell delta T is inversely proportional to 1 by r. That's it. So I hope people are okay with it, right? So it depends on what you are taking the initial and final state. If you make a simple mistake like I did here, then the whole calculation will get messed up. So please remember that. Please be very careful with initial and final states, right? So what are the dimensions that we are going to design? So I guess sir made a simple mistake here, right? He didn't take out the 3 here, or he might have taken out extra 2 here. So that's why there was a mistake here. So I have made this correction. So finally we have arrived to our final relation. And yeah, same goes for this also. Decreasing particle size, the melting point will decrease. Now coming to our favorite topic, phonons. Again, phonons are quasi-particles. What are my phonons? Phonons are my quasi-particles. So phonons are quasi-particles. Collection of vibrating atoms. Okay. So again I will explain that. Heat is transmitted through solids in 3 ways. By thermal vibration, that is the first thing, phonons. By the movement of free metals, or free electrons, right? So first thing you have, phonons, right? Not phonons, should be the heat transfer. Heat transfer. One is through phonons, second is through electron transport through what? Conduction line. And the third is, see again, if these are about matter, whenever you have matter you will have atoms and electrons, and if you do not have matter then that will be a radiation. That's it, simple. So in these 3 ways, and if the material is transparent then you will have radiation, if not then you will have these 2 guys. And if it is metal then this is more dominant, and if it is not a metal then phonons are dominant. And the transmission by thermal vibration again involves the vibration of atoms, and these atoms will vibrate in such a way you will find a wave-like motion. Okay, so these atoms will start vibrating here and there, here and there. So this will look like a wave, right? So of certain wavelength. Then again you can define it has energy E, right? So yeah, and you can even define them as elastic waves, right? Because the atoms, we assume the atomic vibration. So these 2 atoms are vibrating, then we assume this atomic bond as a spring. So that's why we call it as an elastic wave, right? So when a solid is heated, the heat enters as elastic wave, and whenever we say we have a particle and we also have a wave, because we have atoms vibrating as a wave, because atoms themselves we assume them as particles, but when they combine and they start oscillating, they behave as a wave. Please understand, it is confusing, but please. Atoms are particles, we normally assume in classical physics, right? We assume atoms are particles or single particle, okay? And they come together and they form bonds. That's what happens in solids. And if they collectively start vibrating, they will behave as a wave, as an elastic wave, right? And that is called as phone. So heat is transferred as an elastic wave in terms of energy packets, right? So whenever I say photon is a wave and it has the energy. And Planck gave a very good explanation. Photons are wave energy packets or energy packets. The same thing can be transferred here also. So elastic packets, right? Elastic energy or elastic wave energy packets. So, and they travel through material. Now, see, the speed of sound in air is, uh, for example, c naught. Then in materials also it depends upon density, so it should be, almost to c naught, right? So, but do we find the same speed of heat energy transfer in metals? No, it takes time, and the reason behind is the same explanation as diffusion of atoms. Right. So the same applies diffusion of atoms. So we have, because even though the speed of sound is so much large, right? So 343 or 333 meter per second, right? Almost to that range, 330 or 340 range, right? So why can't the heat energy also travel that fast, right? Because the phonons are itself the atomic vibrations. The main reason behind is the scattering of phonons. The phonons can scatter because of the other phonons. It's not single phonon. There are so many phonons inside a solid material. So each phonon can travel a certain distance, and the distance is same as mean free path, which we give in atoms itself when we talk about diffusion of atoms. So the phonon traveling distance, average traveling distance, is given as mean free path. Mean free path is nothing but from starting point to end point, it will not undergo any collision or any scattering with other phonons or electrons or any other particles, right? And that's why the minimum distance, the maximum distance, the mean free path of phonon is 10 to the power of minus 8 meters, right? Which is less than how much? 1 micron is 10 to the power of minus 6 meters, then it should be, so 1 micron is 10 to the power of minus 6 meters. So it is 0.01 micrometer. That's it, right? So 1 micron should be equals to 10 to the power of 3 nanometers. Because micro is 10 to the power minus 6 and nano is 10 to the power minus 9. So minus 6 minus 9, minus 6 of minus 6 minus minus 9, which will be minus 3 plus 3. So that's it. Now so the same, the phonon, so for phonons to move, to define heat flux, we need to define what? So phonon flux. So whenever we are talking about heat flux, we should also talk about phonon flux, because that's how the heat is being transferred. Right. And to write the phonon flux equation, we need to write the heat equation. Now heat conduction, when you see the macroscopically, not microscopically, when you see macroscopically, the heat conduction should be minus K, which is thermal conductivity, times the thermal gradient. Let's only talk about one dimension for now, right? Okay, good. So Q equals to minus K dt by dx. It is not even differential, it is straightforward. Okay. Now this is for macroscopic, when we are not considering anything, we are just seeing the material from above. This is the heat transfer, heat flux. Okay. Now what about the phonon flux? So finally this phonon flux must be equals to heat flux, right? That's how you see the heat being transferred. But microscopically it is done by phonon, right? Macroscopically we defined thermal conductivity, but what about microscopically? That's how we know. Now for example, this is my rod, this is T1, this is T2, and T1 is greater than T2. So you have phonons here, let's write it like this. Now, at every temperature, phonons have some certain amount of energy. Right? When at higher temperature, they will have higher wavelengths. At lower temperature, they will have lower wavelengths. Simple, because energy is inversely proportional to the wavelength. Now, if T1 means the higher thermal energy means higher energy of phonons. Higher energy of phonons means shorter is the wavelength. And if I'm talking about T2, T2 is at lower energy means lower energy of phonons. Lower energy of phonons means very long wavelength. Right? And what do I mean by shorter wavelength? Shorter wavelength is nothing but this. And what is my longer wavelength? Longer wavelength is nothing but this guy. Okay? Now, for example, I have so many phonons here which has high energy. Here, lower energy. And here the energy is decreasing, right, in between. Because, for example, it is T3, then T1 should be greater than, okay, T2 should be less than, T3 should be less than T1. So they have a little bit less energy when compared to the higher energy phonons, but higher energy when compared to lower energy phonons. Now each phonon can travel in 6 directions. What do I mean? Or 6 degrees of freedom, we call it like this. I have X, I have Y, I have Z. This is 3 degrees. There is also negative axis. This is minus Y. This is minus Z. This is minus X. So it can travel in 6 directions. What is the probability of moving in X direction? It is 1 by 6. So the flux motion will be given by 1 by 6. Now let's take a small slit here. Okay, so let's take a small slit. Right? Let's say it has a Lx. Right? This is the flux. So for example, some amount of let's say this is at T. Okay, so let's say if I'm moving in X direction. Now what is the energy? We have defined the probability. Now what is my energy of a phonon? Energy of a phonon will be, here, it is rho Cp dt or T, right? Let's say it is at energy T. Right? Now what happens if it has traveled a distance dt not dt, so the temperature of this range, let's say it is dt, and the same, the temperature gradient is dt here, right? Then what happens? If it is my dt, then what is the flux of phonons that has traveled from here to here? From one plane, let's say this is plane 1, this is plane 2. What is my phonons that has transferred from plane 1 to plane 2? That is given by rho t upon rho x upon x. Right? This is t plus dt. Why? Because at this temperature, let me write everything again so that for better understanding. Okay, so I will draw this diagram here also. I'm only zooming this part, okay? This is my plane. This is a plane 1. This is a plane 2. Now this is a temperature T. Now what is the change in temperature from here to here? That is delta T, and from here to here, that is delta T. Okay, so far so good. There is a change in temperature from one plane 1 to plane 2. Let's say these are at same distance, Lx, Lx. Okay. So for, let's say, because we have said we are only talking about x direction, so it may be the phonons can be moving in either in this way, this is positive x, this is negative x, or they can move in this way. What is my net flux? Net flux will be flux moving in x direction, flux moving in x direction minus flux moving in minus x direction. That will give you a net flux, right? So what is the heat energy at T? Then how do you write? That is rho Cp and T. Right, now the atoms are moving in x direction. Let's say they are moving in this direction. Okay, so then what is the flux of atoms that are moving in that direction? That will be 1 by 6 rho Cp T plus dt by dx times Lx. Now what about the flux atoms moving from here to 1? That can be given as, let's write it like this. Instead of writing all these terms, let's write it. This is from T to 2, this is from T to 1. 1 by rho Cp T minus rho T upon rho x. Then my net flux will be equals to Q T to 2 minus Q T to 1. And that should be equals to this T, that T will go cancel. So 1 by 6 rho Cp, and if you put it the velocity of the phonon here, because we are considering the velocity here also, so then you will have dou T by dou x and Ln. And if you assume this Lx is approximately equals to Ln, that is the amount of distance a phonon can move. And if you compare this net flux to that the initial minus k, you will also have minus here, right? Minus k, because it is moving in where it is moving in negative direction of thermal gradient. Thermal gradient means the temperature is decreasing. Minus k dou T by dou x, and this Tx, these are same, then k should be equal to this term. So thermal conductivity should be equals to minus 1 by 6 rho Cp C0 Lx. That's it. Okay, even when we are trying to derive the drift velocity, we still do the same thing. Even when we were trying to do the derive the flux dou C by dou x, we did the same. D is equals to 1 by 6 the Avogadro number times Z. There was this another term, right? The diffusion term, right? So there was this another term. Okay, let's say omega. So there were some terms which govern our diffusivity. Self-diffusion, there we have studied, but these terms are similar to whatever we are trying to do, the diffusion flux for phonons. We do the same for diffusion flux of atoms in diffusion of solids in phase transformation. If you have read the phase transformation course in metallurgy, then you will have find this. The diffusion of atoms is given by the fixed law, minus d plus c upon rho x. There we do the same thing. The net flux will be same from T2 to T2 and T2 1, minus of T2, right? So that is about that. And moving on to this guy. So the how then what about the nanoparticles? How the thermal conduction take in nanoparticles? So there is this, you have heard the term called quantum confinement, right? And so how do you define your quantum confinement then? And how do these energy values came from the search set, right? So n square, h square, something. So how do you get them? So some of you people might have done the engineering physics. There we have derived, we did Schrodinger, we solved the Schrodinger equation for what? There are many assumptions, right? We assume it is time dependent, independent. First thing, it was time independent, and the second thing, it was what? Yeah, only one dimension. We are not going to do for 3 dimensions because it's just the summation, right? So let's just do it for 1 dimension, so people will understand very easily. Okay? Right. So for example, this is my potential well. This is x equals to 0. This is x equals to L, and whatever my here my only electron is allowable. Okay, this is where, so this is my potential energy is zero, some 0 or constant. Let's do it for 0 because that is easy to derive. Then to take it constant, because if we take constant, then there will be potential energy also, which yes, the potential energy is there from atoms. And we have to consider the potential energy when you are trying to solve the free electron model. Right? You need to consider the potential energy because in metals you have atoms. If you have atoms, then you will have proton. You have nucleus. Then if you have nucleus, then you have positive field around it. Right? So potential. That means you will have positive potential energy. So that is the case. Okay. So for the simplicity, let's assume this. So let's define our function with wave equation psi x, and what is my potential energy? So let's define our potential energy first. So my potential energy is, if, okay, so the first is infinite. If x is less than 0 and it is 0, potential energy is 0 if x is between L, and again it is infinite when x is greater than 0. When you have potential energy as infinite, then it is impossible to find a particle there because the potential energy is so high, the particle will not dare to enter. Right? Because whenever you increase the system of energies, when you try to increase the energy of the system is so high, the system will not remain there. It will try to approach a lower energy system, lower energy state. Right? It will not try to have a high energy state. So that's why you will not find any system there. The same goes for the quantum particle. You will not be able to find the quantum particle there. So yeah, and there is this another term called quantum tunneling. Even though there is a quantum tunneling, you still have some wave function, but it will be a dying wave function. Right? It's not a very good, like there is a high probability of 90%. No, it will be a dying wave function. Okay. So yeah, let's write. So there is no reason to write at these two because you know the potential energy is 0. That means no, not potential energy. You will psi less than 0, 0. Wave function is 0, and we are Then if I try to write my wave equation, what is my Schrodinger wave equation? Schrodinger wave equation is minus h cut square by 2m d by dx square psi x plus, and because of potential energy is 0, I will write it 0, that is equals to total energy of x. It is the energy operator, right? I hope everyone knows. And what is energy operator? Hope. Okay. So I have finally minus h cut square 2m dou square upon dou x square is equals to psi of x is equals to this, right? Now if I write dou square upon dou x square psi of x minus 2m e upon h cut square is equals to psi of x. Now we know this looks like a differential equation. It's not even just a constant. So p square plus k of psi of x is equals to 0. And we know that if I have the differential equation of this type, then my solutions are, then my general solution will be a sine, what is the term there, k, the constant kx plus b cos kx, right? Now what is my k here? K is equals to root of 2me upon h cut square. Now we know p square by 2m, what is that? It is k. Hope everyone knows what is p square by 2m. It's kinetic energy, right? So p equals to mv whole square will be, you will get half mv square. That is a kinetic energy, right? And you also know p equals to h cut k. What is h cut? H cut is nothing but, h cut is nothing but h by 2 pi. Okay. So p is equal to h cut k. Then what is my k square? K square will be equals to root of 2me upon h cut square. I hope it makes sense now. So this p square by 2m equals to kinetic energy. And because we do not have any potential energy, this kinetic energy is our total energy. So p square, in case of p, you will write h cut k. So h cut k square will be equals to that. So k is this. Now, what about the solutions? Now, how do you find the solution of a differential equation? Once you solve a differential equation, you need boundary conditions. Now, what are the boundary conditions? At x equals to 0, let's say, let's remove this part also, okay? For simplicity, at x equals to 0, psi x is tending to 0 and at x less than or equals to 0, and at x greater than or equals to 0, psi because at x is equal to 0, psi of x will be 0. Of x will be 0. Then if I substitute 0 here, so a sin k will be what? So sin 0 will be 0. I will derive everything, okay? So don't worry. Sin k times 0 plus b cos k times 0. So cos 0 1, sin 0 0. Then b equals to 0. position. Then I can write my wave equation as a sine kx. Then what about at x equals to L? At x equals to L, that means x is at x equals to L, also our sine of x is 0, right? So then a sine kl is 0 or not? Yes, it is 0. When is my, if see a cannot be 0, amplitude cannot be 0. If amplitude is 0, then psi function will die down, so it doesn't make any sense. Then this should be 0. If sine k, when can be sine 0? Sine can be 0 only when this kl should be equals to n pi. Then this k will be equals to n pi by L. Then my psi of x should be equals to a sine n pi x upon L. And allowed energies will be, so k will be equals to, and we know what is our wave vector. Wave vector will be equals to root of 2me upon h cut square. This is the potential energy from which we came from. Now the next part is, so k square is equals to 2me by h cut square. It is directly classical relation, there is no complication. And we also got a k relation which is equals to n pi by L. And if I substitute this here, then it will be n pi by L whole square 2me upon h cut square. I want E, allowable energy levels, that is equals to n square now. What is h cut square? H cut square is h square by 2 pi square. H cut by 2 pi. So 4 pi square. You already have a pi square, and you already have L square. There is 2 times 2. So energy will be pi square gets cancelled, n square h square upon 8m L square. So this is what you have seen. So whenever you have this is the allowable energy levels. If n equals to 1, n equals to 0, there is nothing. N equals to 1, this is one energy level. If n equals to 2, so h square 8m square. This is the energy, allowable energy levels. Our electron can only stay here, and the next will be 2h square upon 8m L square, and the next will be 3h square upon 8m L square. These are the only places where our electron is allowed to stay. Not here, not here, not anywhere. Only these black lines. This is the only energy value our electron can have. Right, and according to that you can even derive the wavelength also, right? So if you know E energy, then it is directly proportional to h nu. But hc by lambda is equals to again n square h square on 8ml square. So h will go cancel. So lambda will be 8ml square ml square c upon n square. That's it. Done. So this is the quantum confinement. If you have a quantum confinement, this is the allowable energy levels. If there is no quantum confinement, you can just write it. It has a kinetic energy. Right? So for example, if I am talking about thin films, let's say thin films then my quantum confinement is only in one direction because my other two dimensions are in not in nanoscale. So let's say my z direction is in z direction, right? So what about my x direction? X direction is not simply kinetic energy, the classical kinetic energy. What about, but not the z direction. But for my z direction, it is this. And what about nanorods? My two dimensions are in nanoscale. Let's say my x and y. Okay, then n square h square upon 8 ml x square, n square h square upon 8 ml y square plus ez square. Quantum dot same. So this is how those equations came from. I thought maybe explaining this will help you instead of remembering or mugging things up. So I hope I have explained how the things came and how the derivations, whatever you have seen, which can be easily derived. Even you can try yourself, right? These are not very complex. Okay, so yeah, that's all about for today's session. And if you have any doubts, you can ask, or I will end this session. Let's end the meeting before that.